So we're now to this portion of chapter 16 right here, where we're going to begin talking about weak acids and bases and how their equilibrium constants allow us to calculate things from the pH score to identify them. So just a tiny bit of chemistry in your everyday life. We've been talking about amino acids at the beginning of each one of these. And amino acids, remember, are things that can act as acids because they've got C double bond OH on them, and they can act as bases because they've got an amino group on this side. And these are defined as weak acids or bases. Weak because they only give up hydrogen ions for 1 in every, say, 1 million molecules or so. The other 999,000 don't give up a hydrogen. And I illustrated before how they could act as acids and bases to one another. And so you can think of, with a pH of 6, that 1 out of every million or so give up this hydrogen ion, and then it's donated over here to the amine group over here, forming this thing called a Zwitter ion. This is a good example, and this is also another good example of a weak acid or base. So weak acids or bases, in more general terms, react with water when dissolved in solution to give you some H3O plus and some A minus, or some conjugate base right here. And you can write the equilibrium constant expression for this by writing the products divided by the reactants to the power of the coefficients, and then remember, never put pure liquids or solids in there so water doesn't go into the expression. This K is then given a new name. When it's an acid, it's called Ka, A for acid, obviously. There's a list of many different acid dissociation constants or acid equilibrium constants in Appendix D of your textbook. And you can actually print this at home. Don't print the whole book, it's thousands of pages, but you can print this page, and then on the back side there's even some ones for bases right here as well. And if you can print them back to back, print this page and this page, and then you'll have a handy reference chart to give you lots of Kas for many different acids. And you'll notice that there's many different weak acids right here, and there are actually thousands and thousands of weak acids in the world. This is just a good selection of them. So the bigger the Ka, the bigger the acid strength, because the more H3O plus it forms and the more A minus it forms. And the larger the number here on the top of this fraction, the more dissociation there is. For things like HCl, this number would be thousands, and this number would be very, very, very small. For things like weak acids or bases, though, the number is usually much smaller up here than on the bottom, and you usually get like 10 to the negative 3, 4, 5, 6, 7, 8. The more dissociation, aka the more ionization, the more products you get, and therefore the stronger the acid or the base. And so Ka, or Kb as we'll learn, are good ranking scales for how strong or how weak an acid or a base is. So using Ka, here is an everyday molecule, a little more chemistry in your everyday life. One of the vitamin B molecules in your life is called niacin, and this is the chemical formula or the Lewis dot structure for niacin, and you can see that it's got a scary carbon ring right here, and the little circle in the middle means that it's got resonating double bonds around the carbon with one nitrogen atom in it. But the interesting part of the molecule is actually over here on the right hand side. We have a C double bond OH. This portion right here is what you want to focus on, because this is the acidic hydrogen. This is the hydrogen that can be given away and therefore make this thing called niacin, or vitamin B, one of the vitamin B vitamins, an acid. And a 0.02 molar solution of niacin has a pH of 3.26 at 25 degrees Celsius. Here's our example problem. Calculate the Ka and calculate the percent ionization given this information. So the first thing that we want to do is we want to write a general equation for this and react it with water. And so just like we did with stoichiometry, or just like we did with ice table problems in past chapters, you want to take the acid or the base, and when in doubt, react it with water. And then since it's an acid, you know it's going to donate a proton, so we're going to get our conjugate acid over here, and we'll get our conjugate base over here. And then on the left-hand side, you'll want to put an ICE table, ICE, for initial, change, and end. And we're given enough information in the question that we know the initial concentration of HA to be 0.02. And since they don't tell us anything about the products right here, we have to assume that those are 0. And we don't care about water because water is a pure liquid and it's never in the equilibrium constant expression. Now, when this dissociates or when this breaks up, we're going to give up a little bit of this. We don't know how much that little bit is right now, excuse me, but we do know that at equilibrium, the pH is 3.26. And so we could find the equilibrium amount of this H3O plus right here by using the pH square. And if you look on your pH square, from pH, I can find the H plus ion concentration. And so if I say the pH is 3.26, and I take it to 10 to the negative 3.26, I can find H plus. And so I did this for you, and so it turns out that the H plus ion concentration at equilibrium is 5.5 times 10 to the negative fourth, 5.5 times 10 to the negative fourth. And if you want to write down the work of where I got that, remember that the pH is equal to the negative log of the H plus ion concentration, and the pH is 3.26, and then I solved for H plus right here. So find me. You could write that down if you want to illustrate how I did that work. Since H plus is 5.5 times 10 to the negative fourth, and it's a 1-to-1 ratio between the conjugate base, this is also 5.5 times 10 to the negative fourth, which means I gained 5.5 times 10 to the negative fourth over here, gained 5.5 times 10 to the negative fourth right here, and I lost 5.5 times 10 to the negative fourth right here. And then I did the subtraction for you already, 0.02 minus this 5.5 times 10 to the negative fourth, and that gave me 0.0194. And I think this is a good time to just pause and illustrate to you that this is a weak acid. And weak acids primarily exist over here on this side of the reaction. Same thing with weak bases. And so look at how much the concentration changed from before to after it gave up its hydrogen. You'll notice that both these concentrations are pretty close. I mean, this is 0.019 and this is 0.02. They're pretty close. That means very little went over here to form the H3O plus. Turns out this little bit makes a big difference because it now changes or makes the pH be 3.26. Anyway, back to the problem. We're supposed to calculate Ka, and Ka, or the expression, here's more of my math right here. The pH is equal to 3.26 at equilibrium. The H plus is equal to 10 to the negative 3.26, and therefore the H3O plus is 5.5 times 10 to the negative 4. The equilibrium constant would be the products times one another, so I wrote it as squared, divided by the reactant, which is 0.0194. Divide those two, and I end up with an equilibrium constant of 1.55 times 10 to the negative fifth. And these values, as I said before, are usually available to you on Appendix D, but certain substances won't be on here, like niacin's not on here, and so it might ask you in a problem to calculate what the Ka is. All right, second example problem. This time, let's take a look at calculating the pH of a weak acid solution. So here we're given a weak acid called HCl, and we have a 0.2 molar solution, and I looked up in Appendix D what the Ka of that is, and the Ka of hydrocyanic acid is right here, and it's 4.9 times 10 to the negative 10th right here. So lots of times they don't give you this Ka in the problem. You'll have to look it up in Appendix D, and so that's why I said printing it is sometimes a really good idea. So there's some steps to doing these problems. And so on the left-hand side of the paper, I'm going to write down the steps and then leave at least 2/3 of your paper, maybe more, and we can do the work. So step number 1 to doing these types of problems is to write the balanced chemical equation with water, just like we did right here. And so take HCN, react it with HOH, donate the proton, and then you'll get some H3O plus, and then write the conjugate base over here, Cn minus. So after you've got the balanced chemical equation with water, then make an ice table. Okay, and the ice table would be the ICE right here, and put in the information that you know, which is 0.2 molar for the initial concentration of HCN. And since they don't talk about either of these, put those as 0. And then it says use X. And so you've done these types of problems before, because our goal over here is to find this guy. Because if we find H3O plus, we can get into the pH square. And then once we're into the pH square, we can find H plus. And so use X. And so how much are we going to lose on this side? Well, we'll lose X. How much are we going to gain on this side? X and X. And so at equilibrium, we're going to end up with 0.2 minus X, and then we'll end up with X here and X here. Now, here's the tricky part with this. Instead of making this into a quadratic formula, we're going to make an assumption. Just like we found out in this last problem, that this amount that was lost right here is pretty small compared to the 0.02, because they end up being very similar. We're going to take this X and we're going to ignore it. We're going to ignore that X and we're going to say it's small as compared to 0.2 molar. It's a fair assumption, and I'll show you a way that you can confirm your fair assumption in just a little bit. Next, write the Ka expression, and I want you to write the Ka expression in terms of X right away. So product times product will give you X squared divided by reactant, and here ignore this X, so we'll just divide it by 0.2. Makes it a lot easier to solve, and then set this equal to the Ka that you got from Appendix D, 4.9 times 10 to the negative 10th, and then multiply both sides by 0.2, and square root both sides, and then I can find X, and X ends up equaling 9.9 times 10 to the negative 6th molar. And now that I'm there, I can do step 5, get into the pH square, and look at your pH square. Here's my H plus, and now I want to find the pH, so take the negative log of this 9.9 times 10 to the negative 6th, punch that into your calculator, and I should end up with a pH of about 5. So we can see this is, on a ranking scale, acidic, but not super acidic as well. So these two types of problems are super popular. They're ones that show up all the time as far as calculating goes. And one little aside that I told you I'd give you is, when is it okay and not okay to give this assumption of losing X and like ignoring that amount? Well, then you would calculate something called the percentage ionization. And to find the percentage ionization for this type of thing, you would take the H plus, or the interesting ion concentration at equilibrium, and divide it by the initial concentration of the acid, and then multiply it by 100%. And if this percent ionization is 5% or less, they call that a 5% rule, then you can go ahead and ignore this X. If it's greater than 5%, then technically you're supposed to go back and rework the problem and do it as a quadratic formula. Now, I can tell you that on a test you're never going to have to do that, but you might have to calculate the percent ionization. And so for this, the H plus ion concentration at equilibrium is 9.9 times 10 to the negative 6th. and the HA original was 0.2, and then we'd multiply by 100%. And let's try this on our calculator for a second. 9.9 enter exponent -6 divided by 0.2, enter times 100. It ends up we have 0.0045%, not very much ionization at all. Since it's less than 5%, it's very fair to ignore this X. Last piece in this video cast are acids that have more than one hydrogen. Acids that have more than one hydrogen are called polyprotic acids. More than one acidic hydrogen. H2SO3, H2SO4, H2CO3, H3PO4. These are all examples of polyprotic acids. And therefore, they have more than one Ka. Because once they give up one proton, they're still an acid. They have another proton to give away. So, for example, we can look at our table 16.3, or we can look at the aqueous equilibrium constants in Appendix D, and you can see that they actually list Ka1, Ka2, and Ka3. And so going to one of the acids like carbonic acid that's on our paper right now, you can see that the Ka1 is 4.3 times 10 to the negative 7th, and then the Ka2 is 5.6 times 10 to the negative 11th. And if you look at the trend, you can always tell that the Ka2 and the Ka3 are much smaller than the Ka1. And so the first ionization is always the strongest acid, and then one less hydrogen is weaker, and then if it has a third, it's even weaker yet. As a matter of fact, take a look at phosphoric acid down here at the bottom. 10 to the negative third for the first ionization, 10 to the negative fourth for the second, and for the third it's 10 to the negative 13th. Super duper weak acid by the time you get way down here. These successive ionizations allow something to have more than one Ka, as I illustrated. So H2CO3 would give you this guy, and H plus for a Ka1, and then it would dissociate again and give you CO3 2 minus and H plus and have a Ka2. And as we look them up on Appendix D, they get smaller as they go. And it's always easier to remove the first proton than the second or the third. Polyprotic acids are pretty common. You'll find quite a few of them on the aqueous equilibrium chart right here. And they're tricky because you got to know which one is the Ka, 1, 2, 3, maybe even without seeing the other acid and knowing that, oh yeah, this one could have one more H, and so it's got to be the Ka2. Good luck with your weak acid-base calculations.